Hey, welcome back for part two, the final project instructions. In the first part, we covered how to get your genome and parse it into the individual chromosomes. For this, part two, we're going to go over the rest of the deliverables. So far, you've been able to do enough to get the first deliverable here, that is the Excel file. You'll actually turn that in at the very end on May 7th. We're going to talk about how to get deliverable number 2, 3, and 4 for the rest of this part of the instructions. So we've already downloaded your group's genome, we've parsed the genome for analysis, and now we're going to run Earl Grey on each one of the chromosomes. So each chromosome is going to be analyzed exactly one time, and each member of the group has to analyze at least one chromosome. If there are more chromosomes than there are group members, some of you will have to do multiple chromosomes. And it doesn't matter to me how you split those up. You can decide that within your group. So deliverable number 2 is going to be due on May 3rd. The reason for that is we need the analysis results for each of the chromosomes so that you can complete the last couple of deliverables. That result from each of your chromosome is going to be due on May 3rd, and you'll have to deposit that in the shared directory that corresponds to your group. And this is the path to that directory that has a different directory for each of the groups. So you just put your results in those folders. First step for running Earl Grey on Bridges is to install Earl Grey. So it doesn't come pre-installed on Bridges 2. You'll have to run these 3 commands. ML Anaconda 3 loads the Anaconda 3 module. That will let you run the second 2 commands. So we're going to do conda create, which creates a new conda environment called Earl Grey. And it's going to get the Earl Grey package using the conda forge channel -c means is a specifier for which repository channel to use. So we're going to use conda forge and bioconda. And in those, using those 2 channels, we're going to go get the Earl Grey package. Once that install completes, we'll do conda activate Earl Grey, and that should confirm that Earl Grey has been installed. And what you'll see is, like when you do conda activate from your terminal, you get the little parentheses that say base. That's the sort of default conda environment. If you do conda activate Earl Grey, the parentheses should change to say Earl Grey, and that way you know the Earl Grey environment is active. Second step after Earl Grey has been installed is to move your FASTA files to your personal directory in Ocean. The FASTA files are your genome sequence files. Sorry, not your genome, your chromosome. Right, that was what we parsed in part 1 of the tutorial here. Whoops. So in the example here, my regular home directory is on Bridges 2 is jet home JP Damus. My directory on Ocean starts with Ocean and then projects, bio 2011p, and then my username. We have to move these files onto Ocean because we just don't have enough file space on the primary home directories that were given on Bridges 2. Ocean is the large file system for the Pittsburgh supercomputing environment. From your home directory, if you want to get there over to your Oceans directory really quick, you can use that change directory button, and then you can either copy paste this or type it in. And the only thing that will need to change on this line is that it will be your username right there. And that should take you over to your home directory on Ocean, and you'll see the path should fill in at the top of the page. And this is showing you the on-demand environment for me being logged in. Next step is to create a shortcut to a database of known transposable elements that have already been identified and annotated in the previous Coleoptera genomes that have been published. So from a terminal logged into Bridges 2, you're going to run the command line down here. And this is going to be run. It actually doesn't matter where you run it from because I've got the absolute path. So if you're in your Oceans directory, you can run it, or if you're in your home directory, you can run it. What this is going to do is create a symbolic link to the database that I've already downloaded. So this ln space -s says create a symbolic link. These backslashes say the command is continued on the next line. So when you do the backslash and then enter at the terminal, it shouldn't execute anything. It's just waiting for more information. This first line is the path to the database. So this dfam39 full 13h5, I know it's not a super intuitive name, but that has all of the known transposable elements from Coleoptera genomes. Okay, and then we have another backslash because we're going to continue on to the next line to get the rest of the information for this symbolic link. And this last line is saying where to put the link. And so this is going to go in your Earl Grey installation. So here, the only thing you need to change is this should be your username. So top one, that's the database. I've already downloaded it. It's in my directory, nothing to change there. Second line here, or really the third line of the command, is your Earl Grey installation. So you have to put your username where I've got it bold and underlined right there. Okay. Then when you hit enter after this third line, there's no backslash. And so it should go ahead and execute. And what you should see if you navigate to, like you change directories to this long path here, you're in the famdb directory, you should now see a symbolic link to this file. Okay. And what that's going to do is it's going to allow Earl Grey to go look in this database of known Coleoptera TEs. The reason I'm having you do a symbolic link is because this file is huge. And for everyone to have to copy that, just super wasteful use of resources. So rather than that, I just have everybody point to the database that I've already established. Okay, so why do this step at all? By using the database of known transposable elements, when each of you do your own chromosome, they will all get annotated with the same names, at least for the known transposable elements. Now, Earl Grey is also going to analyze and try to find novel or unique transposable elements to your chromosome or your genome. When that step gets run on each of the different chromosomes, though, there's not going to be any way to tell without extensive work after the fact which families correspond to which, because Earl Grey is giving sort of arbitrary names when it finds a new transposable element. So at this step of using the known transposable elements in Coleoptera is going to at least hopefully give us some standardization of transposon names from one chromosome to the next within your genomes. Okay, next step is to actually run Earl Grey using an SBatch script in your Oceans directory. So I've provided a template script in Canvas, and it looks like this. So you're going to have to download this, modify really just this bottom line. And what it's going to do is submit your job to run Earl Grey on your chromosome. If you want to know all the details of the different options, you can go to the GitHub page. There's a link here, or the Earl Grey paper. The Earl Grey paper is posted on Canvas, but it's also linked on the GitHub page. Just for consistency among all the analyses, I don't want you to modify which options are being used. There are several options presented in the paper about how you might want to pre-filter or post-filter, and we're not going to run any of those. That way I get consistent results for all of the chromosomes across all of the species and all of the groups. If you're running multiple chromosomes, make sure you create a separate SBatch file, so one of these files, for each chromosome. You don't want to add multiple lines to this because this really, depending on the size of your chromosome, it may take several hours to run, and you don't want to have it wait to, say, run 7 hours and then have to do another 7 hours when you could just put it in two different SBatch scripts and have those both run at the same time, so you've got both chromosomes done in 7 hours rather than waiting 14 hours, for example. Move on to, this is what the SBatch script looks like when you download it from Canvas, but you're going to have to modify this bottom line. So I've underlined all the spots where it is modifiable, and it would still work. But Coleoptera, you're going to want to keep the same because we need to go find, the -R says which repeat masker library to go look in. And everybody should be looking in the same one. That's what we set up the, so this database. So when we made this pointer, this DFAM39, it's partition number 13. It has all the Coleoptera in it. And so if you modify this, it's not going to work because we don't have the other databases with any other names, any other organisms in it. So don't modify that. This is just the name of your chromosome file. So whatever when you uploaded your FASTA file, and the fact that mine's named FNA doesn't matter. You can change all of this. It needs to match the file name for your chromosome. The -S is the species name. You can name this anything. It's just going to use it as a prefix for the output files. And then -O says which directory do you want to put your results in. Okay. So here I say // and then it's going to create this directory in whichever folder, right? This says create it in the current folder, the // and so wherever I run this SBatch script, it's going to create this directory and it's going to put all the results in that directory. And then make sure you don't leave off the -T128. So we are reserving one node on the regular memory, one regular memory node on the Bridges 2 system, and we are going to use 128 threads. So we're going to use that whole node to go make these analyses go as fast as we can. Okay. So once you've got that modified so that it's going to run on your data, have this SBatch script uploaded to Bridges 2, so it's in the same directory with your data, and then run it. SBatch and then the file name, and it should it should put you in the queue and then run just like we've done before on the supercomputing with the GVA module. Okay, if the run fails for some reason, so you'll get an email from Slurm when your run starts, and then you'll also get one if it fails or if it completes without failing. If it fails, you're going to want to look at the .o and .e file outputs for the run. These will often give you a pretty good clue what went wrong. If you email us to ask for help on a failed run, our first question is going to be, what do the .e and .o files say? So you might as well look at those and see if you can troubleshoot, because that's what we're going to ask you for. we can't really get anywhere if we don't know why it failed, and these two files will give us at least hopefully a clue for why. And down below here, I'm just giving you an example of what those look like. Um, in the SBatch script, you should have changed this part to name whatever you want to name your job. And so here I ran 3 times without changing the job name. So my job name was Earl Grey libcon1. And then it gives it a .e or a .o. You can see there's 3 sets here. There's a .e and a .o for each of the 3 jobs. And the E has, if errors, if it completes without failing, that's usually blank. So in those 2 runs, there were no errors. Okay. But apparently this one had some errors because it wrote 155 bytes into that file. So that's only if it fails. If it completes successfully, your .o file should have a whole bunch of information, and it's basically everything that Earl Grey would have sent to the screen, it's sending to the .o file. And so you can see the progress as Earl Grey does its analyses. So if the run is successful in the directory that you specified here, right? So you changed this to the output directory. In that directory, you should see that populated by a bunch of folders. And then one of those folders will say summary files. Okay, it'll have your species name, whatever you gave it, and then summary files. Within that directory, you've got all the outputs that you're going to need for deliverable number 2. So you're going to compress this folder using tar.gz into a tar.gz. Hopefully you remember that from back in the Unix section of the course and beginning bioinformatics. Once you've compressed your summary files, you will upload those to the project folder for your group so that everybody has access. Make sure that you, I'm going to actually add something here. Run chmod plus x on your uploaded results. Okay. Need to make sure that everybody has access to this so that they can look in there. And I'll update the PowerPoint online with that information. So everybody in your group should be uploading their results for each of their chromosome, and then name that file, right? Something like that, whatever your chromosome number or accession number is, with the chmod x, so that everybody has access, read, write, execute access on that folder. That way everybody can move it if they need to, download it, so on. Okay. So that your group's folder should end up with 1 file per chromosome, and it should contain all of this information. That's deliverable number 2, and it's due by May 3rd. So the reason that deliverable 2 is due first, so go back here to that original slide, this deliverable number 2 is due first because we need that in order to complete these 2 things. Okay. You don't actually have to turn in deliverable number 1 until you're turning in the final files. Okay. So that's deliverable number 2. Deliverable number 3 is a PowerPoint file with only the following 3 slides. So if you go into Canvas, you'll see there's a template file. And when you download that template file, it basically just has 3 slides in it. The species name and group members will go on the first slide. Second slide has the content, TE content of each chromosome. I'll show you what that's all about. And then the third slide, you're going to have TE landscapes. So that's the template file. To complete it, for the TE family content, you're going to get that from the summary py.pdf files. So here, if we go here, right, this, where's summary pi? Oh, there, right? So if this was your chromosome, well, each chromosome is going to have this summary py.pdf, and you can just open that and screenshot it. That's what I did to assemble this for, I forget which species I was testing this on. If you do it this method, which is by screenshotting the pie charts, you'll get 7 out of 10. Okay. The reason for that is this is not a really easy way to compare if there are any differences among chromosomes. Like it kind of looks like chromosome 1 has more non-TE, that's the black section, so non-repeat content than chromosome 2, for example. But it's not that easy to tell, especially, is chromosome 1 different than chromosome 4? I don't know. They look very similar. So a better way to get 10 out of 10 on this slide is to go to the high-level count.txt output file, right? So if I look in here, it is, oh, there, high-level count.txt. So that middle one. So if you were to open that up, you will see something like this. The updated Earl Grey may have these tables. It's constantly trying to get better, so this might be a prettier table than this even. But it has all the information you would need to turn this into a stacked bar chart, for example. So creating a stacked bar chart like this, where now I can more directly compare the content across chromosomes, that's a way better way to report your results. And so if you can generate this kind of a graph, you will get 10 out of 10 for that component of the deliverables. The last slide in that template is the TE landscape for each chromosome. Here again, I'm just taking screenshots, and that's all you need to do. Take as many slides as you need for this. This is not something that we could compare super easily in terms of generating results, but it is a way to confirm that everybody's results ran and was able to classify the TE landscape. And it's interesting for understanding which transposable elements have been most active, for example. So this, like, if you remember back to the intro material on transposable elements that have lots of copies that have zero divergence, and these graphs are a little strange in that the zero is on the right-hand side of the scale. But things that have more transposons down here that are more similar to each other, like the DNA transposons in this genome, have been fairly active recently. There's not much out here in terms of the old transposons. So the more differentiated they are, the more divergence among copies of DNA transposons, the longer ago they were active in the genome. Here we've got these line elements where there's actually two pulses. So there's a certain probably subfamilies of line elements that were active a long time ago. There's another pulse of active elements and maybe a third one even, but it doesn't look like there are any currently active. Whereas like rolling circles, it looks like there's probably one that is very active right now. And there were some rolling circles that were active a long time ago. That's the way you would interpret a graphic like this. Or yeah. Okay, and then finally, the data to answer research summary questions 9 through 11, and just show you what I'm talking about there. So this is the research summary, also on Canvas. You'll download this, and then you'll answer these each of these questions. So 9 through 11, require you to sort of dig through these results. So here you've got subclass and superfamily. And so we're asking questions like, what has the highest copy number on each chromosome? You get 2 points if you report only by subclass, 3 points if you get subclass and superfamily. So you can, depending on the level that you're able to parse that to, you'll get more points. Okay. And I guess I should also mention that you're doing this deliverable, the PowerPoint file, and the research summary file as a group. I only need one copy per group. So you can divide up the effort however you like. And then that's what this table is for at the end of the research summary. Um, you'll put your name or the names of each of the group members, which chromosomes they were responsible for, and then which other contributions they made. So if they answered or helped answer with different questions or with the PowerPoint, then you would list them there. Okay, so that's deliverable number 4, due on May 7th. Hopefully that is enough to get you going, and get you all the way through. Again, the due dates, the Excel file that I showed in part 1 that's got your chromosome names and chromosome lengths, that's due on the 7th. Then your Earl Grey analysis results for each chromosome have to be uploaded to that your group project file in that location. That's due on May 3rd, right? Got to have that done so early so that you can complete the PowerPoint and the research summary, okay? So that's it for final projects. This is real research, so I hope you have fun with it. And if you run into any problems, be sure to email me or Adam or Zoe.